Hello everyone, so welcome back to my video again. So this time our video is about the three types of antennas. So by the way, this is EC41 module number 8 performance task, and today we are going to discuss about the three types of antennas by Janine J. Panganiban of PSECE 3B. So let's go. Okay, so first we are going to discuss first our first antenna is slat antenna. So slat antenna, it is a type of antenna with an opening cut of a certain dimensions in a metallic conductor which is excited using a two-wire transmission line or a coaxial cable known as a slat antenna. So these antennas operate in the frequency of ranging between 300 MHz to 30 GHz. So it is generally formed by making an elongated slat cut of about half wavelength or half length and with very less than half length in metallic conductive sheet. So the excitation to the slat is provided at the center or of the center. So a horizontal slat antenna provides a vertically polarized signal, while a vertical slat antenna gives the horizontally polarized signal. So let's go to the operating principle. So slat antennas operate on the principle that whenever a high frequency field is present across the slat in a metallic sheet, then energy is radiated. So this is the reason when a slat is cut from the surface of the conductor plate, then on energizing the slat, the electromagnetic wave is radiated, thus acts as an antenna. So due to the presence of a slat, it is named as slat antenna. We can say that a conductive surface with a slat of particular dimensions is referred as a slat antenna. So suppose we have a rectangular conductive sheet over which a horizontal slat is cut having length of over 2 and the breadth extremely less than an wavelength of over 2, let it be into omega. So this half wavelength slat resembles a half wave dipole according to radiation and gain. So however, if the slat antenna and half wave dipole antenna show variation according to the polarization. So the slat antenna, it follows the Babinet's principles. So Babinet proposed that two complementary screens generate a similar diffraction pattern. So this is known as Babinet's principle. So according to Babinet's principle, the structure of the slat antenna and the half-wave dipole structure cut out from the conducting sheet are complementary to each other. So as you can see here in the picture, this is the conducting sheet and this is the slat, and this is the two-wire transmission line. So the region which is cut from the conducting sheet is the half-wave dipole that acts as the slat's complementary antenna. So it is known as the complementary dipole antenna. So this is the current distribution of the antenna. So this basically shows that relativity of the radiated field and impedance of the slat to the radiated field of the dipole. So here the figure below represents the slat and the complementary dipole antenna. Okay, so here are the external feed, which is used as the excitation, is provided at the center of the slot using the two-wire transmission line. So the impedance of the slot antenna relies on the feed point position. So as you can see here, it relies in the feed point position. So as impedance shows reduction with a shift of feed point towards the edge from the center. So here the radiation pattern of the slot and the dipole are similar to each other. However, if the electric field will be vertically polarized for the slot while horizontally polarized for the dipole. So let's talk about the annular slot antenna. So the antenna having a rectangular slot, but it's not necessary to have a rectangular slot only. So as the slot in the conducting sheet can be made in inconvenient shape, so the annular slots are the slots of circular shapes that are present on the metallic sheet. So the ease of construction and analysis highly facilitates making a rectangular or a circular slots. So a narrow beam of radiation is produced by the annular slot antenna. So in this one, we have the slatted waveguide antenna. So in slatted waveguide antenna, multiple slots are present in waveguide, forming a group of antennas. So the separation between each slot is such that there exists half guide wavelength distance between center of each adjacent slot. These slots are cut on the two. Okay, as you can see here, it is cut on the two sides of the waveguide, which is separated the central line. So that it is noteworthy that the guide wavelength is greater than the free space wavelength. Okay, so the impedance of the slot antenna. So the relation between the terminal impedance of slot ZS times ZD is equals to the NO, the N sub O raised to 2 divided by 4. So NO here denotes the intrinsic impedance of free space. And since since our NO is equals to 376.7, so we will substitute the value of NO to our formula. So we will have the answer of 35475.7225. So hence our ZS is equals to 35476 over ZD ohms. So we can determine the properties of the complementary slot antenna if the properties of the dipole antenna are known. So for a half-wave dipole antenna, so we have the ZD is equals to 73 plus I times 42 plus I 42.5 ohms. So then the terminal impedance of a slot antenna will be ZS is equals to our dipole. Our ZS is 35476 or 35476 over to our half-wave dipole antenna, or our properties of dipole antenna, which is 73 plus 42.5 ohms. Then we will going to multiply it to our dipole antenna. Then we will simplify, we will have the answer of ZS is equals to 363 minus I to 11 ohms. So the arrays of slot antenna, or let's go to the applications of slot antenna. So the arrays of slot antenna find applications in aircraft, as the metallic surface of the aircraft allows the formation of the slot directly on it. So they are also used in mobile radar systems. So that's all for our so let's go to our lens antenna. So we just finished our slot antenna discussion. So next is our lens antenna. So what is lens antenna? So lens antenna is a type of antenna that is designed to collimate the incident divergent energy in order to convert it into plane waves using proper lens and materials known as lens antenna. So lens antenna is a microwave antenna that uses the principle of refraction, or utilized by the optical lens for light in order to re-radiate the received energy in the desired directions. So lens antenna operates in the frequency of 1 GHz to 3 GHz. And lens antenna is operated, or it is offered and majorly operating in a high frequency. So it is noted that in case of low frequency operations, the dimensions become very large, so thus the antenna arrangement becomes bulky. So this is the reason these are suitable for very high frequency operations. So lens antenna is regarded as a radiator which operates on collimated action of optical lens. So its operation is similar to reflector antennas. So a reflector antenna allows the energy falling in its surface to collimate in the desired direction. So it results in converting the spherical waves into plane waves. So that is the reflector antenna. So this causes an increase in the diffractive gain offered by the antenna arrangement, or rather for the diffractive gain offered by the antenna arrangement. So it is also similar to a parabolic reflector. A lens antenna is designated to collimate the incident energy which is diverging in nature in the desired direction. This prevents the undesired spreading of the energy, thereby improving the efficiency. So lens operates, so it uses the principle of the converging lens in order to collimate the energy that incident on it. So we are familiar with how a simple optical lens performs collimating action. So we have seen in parabolic reflector, if any one of you has seen in the parabolic reflector, that the energy emitted from the feed element which is present at the focus of the reflector, if it reaches its surface, then it converts the spherically radiated microwaves into plane waves. So it improves the directivity. So in similar way, in case of lens antenna, the point source acts as the feed that emits the microwave energy towards the surface of the optical lens. This optical surface forces the radiated spherical wave fronts to get changed into collimated one. So, in general practice, the collimating lens is made of dielectric material which possesses the indefinite value of the electric constant. But this can also be constructed with materials that exhibit less than unity refractive index at radio frequencies. So it somewhat displays reciprocity theorem that thus is used at the transmitting as well as receiving ends. So let's go to the working of lens antenna. So in the we have discussed the principle of operation of the lens antenna. So let us now see how actually it is designed for transmission and the reception of signal in a microwave frequency range. So in this lens, in this picture, lens in transmitting mode, so let's consider that we have a converging type of optical lens present at a certain position and source from where the energy is to be released is present at the focal point, okay, the focal point here, and it is present at the focal point at the distance of focal length. So our distance here is the focal length. So between the focal point and into the converging lens is the focal length, and along with the lens or along with the axis of the optical lens. So we all must be aware that from the optical point of view, light when falls on the surface of the lens, then it bends due to refraction, and the way of bending of light energy depends on the curvature as well as material from which the lens is made. So as you can see here, the lens axis is here. So going from the focal point, it will travel to the converging lens through the lens axis, and this is the parallel rays of the lens, or the light that travels to the lens, and this is the plane wave front. So when the feed antenna or generally horn or dipole antenna is present at the focal point or at the left hand side, so if the focal point is present on the left hand side, so as you can see here, the arrow is going back to the focal point. So the lens then the spherical wave front emerging, as you can see here, the spherical wave front will emerging from the source, which is diverging in nature incident in the surface of lens antenna. So after incidence, when the rays pass through it, then the diverging rays collimate due to refraction and is converted into plane wave fronts. So if the focal point will going back, so it will emerge into the spherical wave front, or it will convert when it is already in emerging. The parallel rays are obtained at the right hand side of the optical lens. Okay, so when incoming rays is going to the left hand side and the parallel rays is going to the right hand side, the signal from lens antenna using a feed element is transmitted. So in similar way, if this antenna is made of dielectric material, then the radio frequency electromagnetic waves are collimated in a similar way and are transmitted further. So it depends. So it is noted that the converse of the above discussed action of the lens antenna is also true. So consider the consider the below figure here. So here, the parallel rays that incident on the surface of the converging lens converge on the left hand side. So as I said earlier, that it is going to the left hand side of the lens of the focal point due to the refraction mechanism. So this operation is utilized when it is used for receiving mode. So this also shows that it follows the principle of reciprocity theorem. So an important point to be noted here is that to achieve a better focusing properties at radio frequencies, the medium should have a refractive index less than unity. This leads to provide straight wavefronts even when the refractive index of the material is high or low. So let's go to the types of antenna. So we have two types of antenna. We have the delay lens antenna and the fast lens antenna. So delay lens antenna, the type of lens antenna that causes retardation in the traveling wavefronts due to the lens media. So it is known as the delay lens antenna. So these are sometimes known as dielectric lens. And the reason behind this is that due to the medium of the lens, the electrical path length is increased and the wave undergoes retardation. So as you can see here in the figure, so the medium of the lens, so from source it is going to the dielectric lens, but it is slower. So it has a delay lens antenna. So that's why it's called delay lens antenna, because it is the spherical wave front is traveling from a slower action into the dielectric lens. This is also classified into two categories. It is a non-metallic dielectric lens or the metallic dielectric lens. So as our example, it is based on the type of dielectric material. So for the fast lens antenna, in this type, the traveling wave fronts are speed up by the lens media. So as you can see here, the wave fronts here are faster to travel than to the delay lens antenna. It is also known as the E-plane metal plate antenna. And okay, so this is the fast lens antenna. As I said earlier, that it travels faster than the delay lens antenna, and it is also called the action E-plane metal plate lens or antenna. So let's have the advantages of lens of antenna. So unlike the parabolic reflector in lens antenna, the aperture of the antenna is not obstructed by the feed point. It offers more flexibility in design tolerance. This means twisting in a lens antenna is possible. This is due to the reason that wave incident at one side and emerges from the other. It is used for very high frequency applications. Okay, so let's have the advantages. The low frequency use of lens antenna makes the antenna arrangement heavy and bulky. These antennas are more expensive than reflector antenna for the same gain and bandwidth. So these are wideband antennas that are referred as microwave antennas and are suitable for frequency above 3 GHz. So the electric lens antennas are frequency sensitive. Thus, this specific type is not used over the wide frequency range. So that's all for our lens antenna. So let's move on to our next topic. Oh my gosh. Okay, so let's discuss the Yagi-Yuda antenna. So this is a commonly and well-known antenna. The Yagi-Yuda antenna. So from the name of it, it came from Japanese, from Japan. So Yagi-Yuda antenna is well known for its high gain and directivity. Yagi-Yuda antenna is formed by a combination of three major elements. In example, driven element, reflector, and directors. So Yagi-Yuda antenna operates in a very high and ultra-high frequency from 30 MHz to 3 GHz. So let's have the little bit of history from Yagi-Yuda antenna. So Yagi-Yuda antenna was named after two scientists from Japan who developed and explained this antenna. So Professor Shintaro Yuda initially explained the theory of this antenna in the Japanese language in the year 1928. However, later this antenna was explained in English by Hidetsugu Yagi. The English explanation of Yagi-Yuda antenna made the theory worldwide famous. But as the antenna was initially proposed by S. Yuda, so on behalf of contributions made by both of them, the antenna is given an appropriate name known as Yagi-Yuda antenna. So it is sometimes known as Arial or Yagi antenna. So this was developed in the year 1928 but is adapted for personal and commercial use since 1930. So Yagi-Yuda antenna has three main elements that combinedly form its structure. So these three major elements are a driven element, which is generally a half-wave folded dipole, a reflector, and a directors. So the structure contains one driven element and a reflector, while directors can be more than one. So as you can see here, this is the clamp and this is the feed line. So we have the insulators here. So this is the insulators. And we have the reflector, as I said, the three elements. We have the reflector, director, and driven element. So the director is composed of two. Okay, they have the two director, one element, one driven, and one for reflector. So basically, the arrangement is said to be an array of active and parasitic elements. So the dipole, generally a metallic rod, acts as the active element. Okay, and external feeding is provided to it using transmission lines. Then, while reflector and directors are the parasitic elements of the structure, the parasitic elements are also metallic rods placed parallelly in the line of sight orientation and with respect to the driven element. Okay. So, the external excitation is provided to the parasitic elements. However, when the dipole is excited using a transmission line, then the current that flows through the driven element induces voltages in the parasitic elements. So all these elements are mounted on a center rod that acts as horizontal support. Okay, so the reflector present the reflector is present at one of the ends of the metallic rod and has a length of 5% greater. Okay. So it has a length around of 5% greater than the length of the driven element. So as you can see here. So here is the reflector and here is the driven element. So while the directors are almost 5% shorter than the driven element. So in example, the half length at the resonant frequency and are placed at the other side of the dipole, as these are used to provide maximum directivity to the antenna. So for 3 elements areal, the lengths of the elements can be considered as, okay, so the length of elements, we have the length of driven element is equals to 475 over FMAZ 10 times feet. And for our length of reflector, we have the 500 over FMAZ times feet. Then length of director is 455 over FMAZ HZ times feet. So for the working of Yagi-Yoda antenna, so we know that external excitation is directly provided to the active element of the arrangement. In example, the dipole. So the flow of current through the active element induces a voltage in the parasitic elements that cause current to flow through it. The element having a length greater than half length, in example the reflector, shows inductive characteristic. Therefore, the current in the reflector lags the induced voltage. So whereas the one shorter than the half wave dipole, in example the director, is a capacitive. So the current flowing through it leads to voltage. So as you can see here, so as we know that the director is placed in front of the driven elements, so it is placed in the front of driven elements, okay, here. So these directors add the field of the driven element in the direction away from it. So when multiple directors are placed in the arrangement, then each director will provide excitation to the next one. So here is the length, and here's how the Yagi-Yoda antenna work. How does the work for it? So the reflector in the opposite direction is that of the director when accurately placed adds the field in the direction towards the driven element. So this is done in order to reduce the losses due to the back-radiated wave as much as possible. So in order to get the additional gain, multiple directors can be used in the direction of the beam. So let's have the spacing between the elements to form a Yagi-Yoda structure. So spacing between the elements is, so the spacing between the directors is 0.1 to 0.3 wavelength. So we have the for the reflector and driven element is 0.23 to 0.35 length. Then the spacing between the driven element and the director is 0.125 to 0.15 length. So basically the induced voltage and the current flowing through is due to the induced voltage in the element varies with the spacing between the active and parasitic elements, along with the reactance associated with the elements. So it is here that with the increase in distance between the driven element and the director, there will be more need for capacitive reactance in order to provide accurate phasing to the current in the director. So the length of the director is kept small to get the capacity reactance. So Excitation to the driven element is provided using feed lines. So this causes the emission of radiation from a reflector towards the director. Moreover, a portion of the emitted radiation excites the parasitic elements, so that further re-radiate the radiations. So the length of the elements and the spacing is a great importance here because radiated energy from each element gets summed in from the front direction and so cancels the back radiated wave. So let's have the characteristic of Yagi-Oda antenna. So Yagi-Oda antenna is said to be a beam antenna if it is only three elements array, in example driven and reflector, and only a single director. So it offers a moderate and directional directivity. The gain offered by the Yagi-Oda antenna is around 8 decibels with front to back ratio of approximately 20 decibels. And in order to increase the directivity, more elements can be added in the array. And another is name to this antenna is super directive antenna due to its high directive gain. So the frequency sensitive thus is a fixed frequency device. So let's have the radiation pattern of Yagi-Oda antenna. So the radiation of Yagi-Oda antenna is, as you can see here, the minor lobes and the major lobes. So the minor is smaller than the major lobes. So the major lobe represents the forward radiated wave, while the major lobe represents the back radiated wave. So the advantages of Yagi-Oda antenna is it offers a very high gain. So that's the number one. Then second, it possesses a highly directional characteristic because of the use of directors. Third, it is a low cost antenna. So that is why it is also a well-known antenna and a famous antenna. So Yagi-Oda antenna shows suitability towards high frequency operations. Then fifth, it is a light in weight and feeding mechanism is also simple. 6, it is a power efficient. And 7, along with all the above defined advantages, it is also offers ease of construction and handling. Let's have the advantages of Yagi-Oda antenna. So these antennas are highly affected by atmospheric conditions. So it depends on the atmosphere. Okay, if it is also second, noise is the major factor that disturbs the overall performance of the antenna. So sometimes if it is raining, so the antenna cannot perform the exact performance that it should have. So sometimes when it is raining, the signal that the Yagi-Oda antenna is transmitting, it causes a lot of disturbance. So the applications of Yagi-Oda antenna. So these antennas are widely used in the field of TV signal receptions. So as it has excellent receiving ability, even astronomical and defense related applications make use of Yagi-Oda antenna. Also, radio astronomy utilizes these antennas. So that's all for today. Thank you for watching my videos and God bless.